So we are starting with another topic, which is normal, Poisson and binomial distribution under the probability distribution. So here's the flow. So what is probability distribution? See, probability distribution gives the possibility of each outcome of any random experiment or event as it provides the probability of different possible occurrences. If we recall, we studied earlier, like what is probability, then it's a measure of uncertainty of various phenomena. Like if we throw a dice, the possible outcome of it is defined by the probability. Now, in the probability distribution, it could be defined with any random experiments whose outcome is not sure or could not be predicted. And thus, it specifies the probabilities of various possible values or ranges of values that a random variable can take. So what are the types? There are mainly two types, discrete probability distribution and continuous probability distribution. Discrete probability distribution is where the random variable can take on only a finite or countable infinite number of distinct values. Example under this comes as a binomial distribution or the Poisson distribution, like where the value of x can be fixed, maybe 1, 2 and other numbers further on. Whereas in continuous probability distribution, the situation is when the random variable can take on any values but within the given range, and usually they are the real numbers. For example, this includes normal distribution or the exponential distribution, where the value of x can be given under the range of like between 0 to 1 and 1 to 2, then 2 to 3 and further on within a given range. So this is the basic difference between the two. The major two properties of a probability distributions are given above, where it says the first property says that the possibility of all possible outcomes, the sum is equal to 1 always, and the other is linked to the first one, where it says that the probability of each outcome must be between 0 and 1, that is inclusive of it. Now, based upon the types of probability distribution, that is discrete and continuous, we'll now study these distributions. Like we studied under the two different examples, normal, Poisson and binomial distribution. So we'll start with them now. So we'll start with the normal distribution, which is normal distribution, and it's also known as the Gaussian distribution, and it is the most symmetrical bell-shaped distribution where the probability distribution is shown to be symmetrical about the mean, which means that the data near the mean is more frequent in occurrence than the data which is far from mean. So that is why it takes this bell shape. As we already know that it's a continuous probability distribution, and they are usually very much used in statistics and also are often used in natural and social sciences to represent the real valued random variables whose distributions are not known. Now, what are the chief characteristics of this distribution? The very first is the symmetry. As you can see in the figure, there is a kind of a symmetry because this distribution is symmetrical around its mean, which is mu. This means that the values on the left side of the mean are the mirror image of those on the right side. Here in the figure, you can see the point 0 is the point of the mean where it's taking its peak. That means the values are mostly centered around this point. Mean, which is represented as mu, is the central point, like I said, at point 0 in the figure you can see and match, and it is at the peak, and that's why it takes this bell curve shape. It is the average of the data. The next is standard deviation. It shows the deviation, meaning to say how much the data is dispersed or spread from its mean position. So, this itself means that a smaller standard deviation means that the data point will be closer to the mean, whereas the larger standard deviation will mean that the data points are spread out and are farther from the mean value. And the next is the bell-shaped curve, as we already studied a little about it, that the graph of this normal distribution is bell-shaped. Why is it so? Because the highest point is at the mean, because most of the data is centered around the mean. The tails of the curve approach but never touches the horizontal axis, the x-axis, and it extends infinitely in both the directions. The next is 68, 95 and 99.7 rule, where the first 68 means that about 68% of the data falls within the one standard deviation where the mu is plus minus to that of the mean. Then the 95 means 95% of the data falls within the 2 standard deviation, that is mu or the mean value is plus minus to 2 standard deviation. And 99.7 means 99.7% of the data falls within the 3 standard deviation where mu is plus minus to that of 3 times of standard deviation. That we can see in the next slide. The figure is given there. So let us see the figure here. We can see that the one standard deviation which is where on both the sides the equal percentage of distribution is there, that is 34.1% on the right hand side and 34.1% on the left hand side, represented by the first standard deviation, one standard deviation, which is 1 sigma on the right and minus 1 sigma on the left. This is the Greek sigma where it is used for the standard deviation. Similarly, for 2 sigma, it's 13.6%, and similarly on both the sides, it's 13.6. So the first or the one standard deviation takes 68.2% area, whereas the second one is spread around 95.4% area. And similarly, if we see that for the third one, which is 3 sigma on the left and minus 3 on the, 3 sigma on the right and minus 3 on the left, which is taking around 2.1%, is spread around 99.7%. So that is how, even with the help of this, we can find out the value of z here, which we'll further study under the numerical parts. So now what is the probability distribution function here, since it's a continuous distribution? So PDF or probability distribution function is used to specify the probability of a random variable falling within a particular range of values as opposed to taking any one value. The probability is given by the integral of this variable's PDF over the range, that is given by the area under the density function but above the horizontal axis, x-axis, between the lowest and the greatest value of the range, like we just saw. The probability density function, this PDF, is non-negative everywhere. That is the thing. So it cannot take the negative value. And the area under the curve is equal to 1. The formula is it's the function of the random variable x, the mu, which is mean, and sigma, Greek sigma, which is standard deviation. It is calculated as 1 upon sigma under root 2 pi, where the value of pi is given. E exponential, the value of E will also be given. It's constant, multiplied by under bracket minus x, which is the random variable, minus mu whole square upon 2 sigma square, and the brackets are closed. The value of E and pi are given and known. Now comes the next, which is the Poisson distribution. So it is a discrete probability function. That means the variable can only take specific values in a given list of numbers. That can be probably infinite. A probability distribution measures how many times an event is likely to occur within certain x period of time. Or we can say that we can define it in other way as the probability distribution that results from Poisson experiment. A Poisson experiment is a statistical experiment that classifies the experiment into mainly 2 categories, can be success or failure. And thus Poisson distribution is a limiting process of the binomial distribution. A Poisson random variable, which can be defined as x, defines the number of success in the experiment. And this distribution occurs when there are events that do not occur as the outcome of a definite number of outcomes. So it is usually used under certain conditions. That is the number of trials n tends to infinity. That is, the number of trials are so much that they can go till the infinity. Probability of success, which is usually denoted as small p, tends to 0, and their product, which is NP, is equal to 1, which is finite. So these are the three conditions under which this exists. Now if we talk about the nature of these events, then they needs to be independent of each other. The rate at which the event occur shall be constant, that is, event happen at a steady average rate, and two or more events cannot occur at exactly the same time, or they needs to be exhaustive by nature. Now it can be used at a place where, as we already saw, that the event can happen infinite times, like the number of emails received in an hour, or number of accidents on a road in a day, or number of phone calls received at a call center. There this Poisson distribution can be used. Now we'll see the formula part. So the formula is P x, which is equal to k, capital X, which is equal to small k, is the probability of observing exactly k events, is equal to lambda to the power k multiplied by e to the power minus lambda upon factorial k, where lambda is the average of events, rate parameter. Here the value of E is Euler's number, which is a constant which will be given, and K is the number of occurrences. We'll pick up a few numericals in the next video, as this video is already too long for them. So we'll pick up few examples of how these formulas can be applied to solve a numerical problem. The formula we just saw itself defines the key characteristics of this distribution, that the parameter lambda is the mean number of events that occur in a given time or space interval. As it's a discrete distribution, it is both the mean and variance of the distribution. This lambda represents both. Now, as we know, it's a discrete distribution, meaning to say that it models countable events, like we can number them into 0, 1, 2, 3, etc. The distribution will be rightly skewed. It will be skewed towards the right, especially when the lambda's value is small. As the value increases, the distribution becomes more symmetric, like the normal distribution, as we saw, where it's equally distributed on both the sides, that is towards right and left. So it tends to take that normal distribution shape. And the next characteristic is that the Poisson distribution assumes that the probability of event occurring in a given interval is not affected by the previous intervals. They are exhaustive by nature, and thus they are known as the memoryless distribution, or the events. As we can see in the figure here that as the value of lambda is increasing, the distribution is becoming more and more symmetrical, and it's approaching towards the normal distribution. That's been shown here. As we can see here, the value of lambda from 6, then 12, further 18 and 24. So the more it's increasing, it's tending towards the normal distribution by nature. Now there is an example given of where you can apply the formula, if you have a call center where on average 3 calls come in an hour, that is lambda becomes 3. We can use the Poisson distribution to calculate the probability of receiving exactly 5 calls in an hour. So what we'll do, we'll simply put the values here. So here we'll put the values. Lambda becomes 3, K becomes 5, E's value is already given, which is a constant. So the value comes out to be approximately equal to 0.1008, which means that there is approximately 10.08% chance that exactly 5 calls will come in during that hour. So that is how it works, and that is how it is applied to find out. Now comes the next distribution, which is binomial distribution, as the name itself uses the term bi, which means 2. So it is the discrete probability distribution that gives only 2 possible results in an experiment. That can be either success or failure. For example, tossing a coin, that could be 2 possible outcomes with head or tail. And if any test is taken, there could be only 2 results, either pass or fail. So the distribution is also called as binomial probability distribution. There are mainly 2 parameters which are used here, small n and small p. The variable n states the number of times the experiment runs, and variable p tells the probability of any one outcome, the success rate. Suppose a die is thrown randomly 10 times and the probability of getting 2 for any one throw is 1:6 because there are 6 heads. As already discussed, the key parameters are small n, that is the number of trials, p the probability of success on each trial, and q is the probability of failure in each trial, which is equal to q will be equal to 1 minus p. So that is how it can be calculated also. The probability mass function can be found out by the formula n factorial upon k factorial multiplied by n minus k factorial, where the k is the number of events and n is the number of trials. So k is actually the event that we want to find out, or exactly the successes in n number of trials. So this is how the coefficient is worked out. The property says that mean will be mu will be equal to the product of n and p. We already know what n and p are. Variance will be the square of standard deviation, which is equal to the product np in bracket 1 minus p, where the standard deviation or the sigma is under root np in bracket 1 minus p, or we can say npq, under root npq. Now an example is taken here to explain, like if you flip a fair coin 5 times, the probability of getting exactly 3 heads, that is the success which we want, can be calculated using this binomial distribution. How? Because here see, small n would become 5 because the coin is flipped 5 times. P, which is the success rate, as the success rate is half or 0.5, would become 0.5, and k, the k that we need, the head success rate is equal to 3. So we'll simply put it into the formula to find out the value. This one is taken here just to show how binomial distribution is plotted using the bar graphs. Here the condition is that the value of n is 18 and the value of p is ranging between 0.1 to 0.75. So that is how it's been plotted here. The 4 conditions are given. In first the p is 0.1, then it's 0.25, then it's 5, and then it's 0.75. So under the 4 condition, how it's been plotted, that's been shown here in the diagram. So that was it. Let's meet in the next tutorial video. Till then, take care.